Welcome to this channel, Aspects of Industrial Automation. In this video, we are dealing with first-order systems in control theory. The idea behind is to be able to simulate with Siemens software TIA Portal a first-order system, constructing a simple mathematical model that can be programmed into the TIA Portal software. That way, we're going to have a block that mimics the internal structure of a first-order system, and then we will be able to build higher-order systems. Then we could connect this model to a controller, for example, a PID controller. But this part will be discussed in the next video. For the time being, however, we will start reviewing what a closed-loop first-order control system is. This figure illustrates a closed-loop system, a simple one, the main part being the plant or industrial installation of part of it, which produces one or several variables to be controlled or to be regulated. In the simplest case, only a variable will be considered here. In this example, the plant is a heat exchanger. The substance to be heated could be, for example, an oil with an input temperature that is called here T-in. The oil enters the heat exchanger here on the left, is heated inside the plant, and comes out here as product out with a higher temperature T-out. In order to be able to control or regulate the temperature, the first thing that should be made is measure it. The control variable, identified here by the letter C, is read by a temperature transmitter, TT, and is directed to the controller. The measure variable is called B, and this is the variable to be controlled. In the controller, the first part is a summing element. The measure variable is compared with the so-called set point or reference value. The reference value is subtracted from the measure variable or the other way around, and the difference between both variables is called their error. When the set point or reference value is exactly equal to the measure variable, the controller has no further action to do. But in the case that the reference value is different than the measured value, then an error is produced, and this error is directed to the so-called final control element, in this case a valve that lets pass water vapor in a certain quantity in order to interact with the incoming oil and heat it. As an example, suppose that the reference value is 70 degrees Celsius and that the output temperature is lower, for example 65 degrees. That means there is a difference, a positive difference between the measure value and the set point. Set point 70, measure variable equal 65, that gives an error of 5 units. That means that the controller has to act upon the valve and, for example, open it a little bit in order that more vapor can enter the system and more energy is interchanged between the incoming oil and the vapor, and as a result the temperature of the product and the output is going to be increased. On the contrary, suppose that the output temperature of the oil is greater than the set point, for example 72 degrees here the output, and the set point is the same as before, 70 degrees. In this case, the difference between set point or reference R and measure variable B is negative and has a value of 2 units. In this case, the value of 2 units is negative, and the valve should be, in this case, closed a little bit so less vapor enter the system, and therefore the temperature of the oil can be reduced a little bit until it reaches or approaches the set point. This is a physical representation of a closed loop system. It is closed loop because there exists a feedback between the measure value and the controller, and then this feedback is transmitted to the final control element. In the practice, and in order to be able to simplify the analysis of those control systems, it is more convenient to use so-called block diagram representation. In this block diagram, the same parts as in the physical system are considered. For example, the plant, the heat exchanger, is here in this blue block, and inside is a mathematical transfer function that relates the output to the input. If we start with the plant produces the variable to be controlled. This is the plant output, and this variable is directed to the feedback part. This is the temperature transmitter or the measuring instrument. The variable is measured, and this value is directed to the controller. The first part of the controller is a summing element, where, as before, the set point or reference value is compared with the measure or value to be controlled. The difference between both of them is the error, which is in turn processed into the controller and further applied to the plant in order to correct for any variation with respect to the set point. Now we're going to consider the simplest system in control theory. This is the first order system. A first order system is a control or mathematical system that can be described by a first order differential equation, whose higher order derivative is d with respect to vt. In order to analyze a first order system or any other kind of system and determine the time response, standard inputs such as a unit step function, ramp, or even sinusoidal signals are usually used. The response can be to a unit step and can provide important information about the dynamic behavior in time of the system. In this example, on the left part of the graphic, we have a step response, a signal that comes abruptly from 0 to 1, for example. This is fed to the plant, and there is a response that could be, for example, an exponential function that approaches asymptotically the final value of the response. A typical example is a simple electrical circuit with a resistor R and a capacitor C. There is an input voltage called VI here on the input and an output voltage V output or VO. If we apply a step function here on the input, for example, a voltage that goes very fast from 0 to 1 volt, we will see that the output voltage will have approximately this behavior, because the capacitor has to be loaded and it is not possible that it loads immediately. The equation in the time domain relating output voltage to input voltage is this one here. Output voltage equal input voltage times 1 minus e2 t divided by RC, being RC the so-called time constant. Units of R times C are seconds or any other time unit. An important consideration of these systems is what happens when we let the time run. For example, when t, the time, tends to be a great value, tends to infinity, mathematically speaking, what happens? This is going to be the so-called steady state value of the voltage across the capacitor. And in this formula, if we let t tending to infinity, the output voltage is going to be exactly equal to the input voltage. This can be easily seen if we substitute t by infinity in this exponential term. Mathematically, it is simpler to analyze and treat this control system not in the time domain but in the so-called Laplace domain, where the time variable is substituted by the so-called Laplace S particle, which is equal to j omega, j being square root of -1, the imaginary number, and omega, the angular frequency. Without entering the details of converting a certain term in the time domain into the Laplace domain, when we have a constant, like here the number 1, and convert it from time to the Laplace domain, the constant will be divided by the particle s. I1 corresponds to 1 divided by s, and the exponential corresponds to this term. Exponential t divided by rc in the Laplace domain is 1 divided by s plus 1 divided by t, where t is the product of rc and is called the system constant. This value that makes the denominator of this expression equal to 0 is also called the pole of the system. The poles are the values of the transfer function that make the denominator equal to 0. Processing the previous equation, we obtain the transfer function output voltage divided by input voltage equal to P, the pole, divided by S times S plus P as the Laplace transfer function due to a unit step. In general, a transfer function of a first-order plant is given by this expression: G equal to K, S plus Z, Z being the so-called 0, divided by S plus P, P is the pole, when this is equal to K, quote, 1 plus S times T1 divided by 1 plus S times T2. 1 divided by T1 is the 0, and 1 divided by T2 is the pole of the system. For programming purposes, and this is going to be valid when we insert this equation as a model in the TIA Portal Siemens program, we have an algorithm or formula or equation that relates the output of this first order system or first order function with its input in. In this formula, in is the input to the plan or compensator, because this transfer function is usually called also a compensator, since if we connect the compensator to a controller, we can alter the phase and the amplitude, and we can manipulate those values. Out is the output of the plant, LG time is the lag time, and in the formula corresponds to the pole of the system, 1 over T2. Sample time is the sample time of the algorithm, or inverse of the frequency at which the algorithm or formula is processed. Previous output is the output of the previous cycle, the cycle n-1. Gain is the gain, as the name implies. LD time is the lead time and corresponds in the formula to the 0 of the system, and previous input is the input of the value that the plant had in the cycle n-1. And once we have the model or algorithm for the first order system, we can connect two or several of those first order systems in series, and then we obtain a second order or a higher order system transfer function. In case of a second order system, like in this figure, it has 2 poles and 2 zeros. In the next video, we are going to consider second order systems connected to a PID controller. But in this video, we're going to work only with first order system. That means a system with a gain K, a pole, and a 0. And now we are in Siemens TIA Portal software, and the first thing we have to do after constructing a PLC variable table is to create a block, for example a function block. I have already created the block. The block is FB1 and the name is lead lag block, and this is the interface part of the block where the formal parameters are defined: inputs, parameters, output, static variables and temporary variables. As input parameters for the algorithm, we have the int value, the lead time, the lag time, the sample time, and the gain. All these parameters are of data type real. Those are real values. Output is only one, is the output of the system, of the first order system, and is real type as well. We also have two static variables, in previous and out previous. And why have we defined these variables as static? Because we don't want these variables to be erased when the program finishes. If these variables disappear when the program finishes, then we don't have its value, its n-1 value for the next cycle. Defining the variables as static, they are stored in the instance data block and they don't get lost. And three temporary variables, numerator 1, 2, and 3, and denominator, and all of the variables, as you can see, are of data type real. Getting back to the algorithm, we note that it has three terms, first term, second term, last term, and all of them has exactly the same denominator, lag time plus sample time. The numerator are different, but the denominator is the same. Now back in TIA Portal, we can then program this formula or equation using the so-called SCL language, Structured Control Language, which is much more appropriate for algorithms and formulas than the classical ladder language or even the function block language. In the first line, we calculate the denominator equal to lag time plus sample time. Then we calculate the three numerators corresponding to the three parts of the algorithm. Numerator number 1 is lag time plus out previous. Numerator 2 is gain plus lead time, sample time multiplied by gain, and this in turn multiplied by in. And the third and last numerator is equal to gain multiplied by lead time multiplied by in previous. Then the output of the plan is the sum of numerator 1 and numerator 2 minus numerator 3 divided by the denominator. And at the end, we prepare the output and input values as output previous and input previous for the next cycle. That way, the algorithm is programmed, and we can close this window, and now we have to call this block, but not from the main program OB1, but rather from a cycle program. For example, the cycle interrupt OB 30, 31, 32, etc. We can choose the number 30, which is called by the operating system every 100,000 microseconds. That is equivalent to 0.1 second. This is the standard value. And normally, when we work with PIDs or controllers, these blocks, because of their complexity, are going to be processed not in the main OB1 block, but rather in cyclic interrupt blocks like this one, OB30, 31 to 38. We validate this window, and then we can call from here the lead lag block, FB1. We move that over here, and because this is a function block, it needs an instance data block. We can use this by default, the number 1, with the name lead lag data block. Then we have here on the left hand side the inputs, parameters, and the right hand side the only one output parameters. Input, we can put here, for example, MD100. This is a double word, and I have already declared it in a PLC variable table. This is the input of the system. Lead time for the moment being, let's put 0.0 seconds. Lag time, for example, to begin with 15 seconds, sample time 1, gain also 1, and the output will be empty, for example 104. This is also a double word for a real variable, and the variable is called process variable. Now we have the block already programmed, and we can check it with the simulator, applying an input here on the int variable, and this could be a step input. For example, initially is the input at 0.0 value, and we apply a 1.0 value immediately. Okay, in order to check if this is going to function properly, we click here and shows the simulator, load in the PLC, finish, and we got it. We move this simulator here to the right, press run. Okay, and remember that the lead time is 0. It means that the 0 of the transfer function doesn't exist. The transfer function has a gain in the numerator and no 0, and has a pole which is related to this lag time. Okay, next step is to animate monitoring on. The program is already running. Everything here on the left hand side is green. That means offline program and online program are exactly equal, and we have here the input value 0.0, output also 0.0. What happens if I force or modify a value here on the input? Instead of 0.0, I write a 1.0 value. This corresponds to a step input. Right click, modify operand, I move this here 1.0, and when I click on OK, you will see that the output is going to try to follow the input. In the beginning at a fast rate, and then as the output approaches the input, that is the value of 1, the time response gets slower and approaches asymptotically the one that I'm going to force here. Okay, and you see the result, null. Okay, we are almost at 1. It has lasted a few seconds from the time I put the 1 here to the time it has reached practically the value of I. 0.999. We have 0.99999. This is practically 1. If I reverse the input, modify operand, and then I put here again 0, what's going to happen? Exactly the same, but in reverse order. The output is going to try to follow the input, which is 0, in the beginning very fast, but at the end it will approach the input slowly. Here you see, from 0.9 to 0.02, 0.01. It depends on the parameters here, on the gain, and of course on the lag time. What happens if I modify the lag time? Instead of 15 units, I put, for example, 2.0 units. 2.0 units is a very short time, but because I've changed a parameter here, I have to load this again. I don't have the green ball here on the left. Then I click on cycle interrupt and press here to download to the system, load into the PLC. Okay, we have now 0.0 and 2.0 as lag time. Okay, we have here 0 at the output, 0 at the input, and observe what happens if I modify again operand from 0.0 to 1.0. Okay, we'll see that the output is going to be much faster than before. In practically 1 or maximal 2 seconds, the output has reached the input. And the same if I modify it back to 0.0. 0.0, I press on OK, and in a matter of 1 or 2 seconds we have already 0. 10 to minus 17, minus 18, this is practically 0. Okay, I will let the lag time as before, 15 units, but I'm going to change the gain from 1.0 to say 2.5. What happens? Okay, first of all I have to load the whole program, or this block in particular, again into the PLC. Load again. Okay, we got it. And now I will force here again a 1 again, and observe that the lag time is exactly the same as at the beginning, 15 time units. I have only changed the gain from 1.0 to 2.5. When I validate this window, you see that the output is going to be slower than when I put here 2 units of time, but in this case the output is going to follow the input. The input is 1.0, but the gain is 2.5. And if you remember in the equations of the transfer function, the transfer function depends proportionally to the gain. The gain was the factor k. K was 1.0, but this time it's 2.5, and that means that the output will tend to 2.5. This moment is 2.499998, that is practically equal to 2.5. Okay, I return again as before 1.0. Okay, I have already loaded the program and have also applied a 0.0 value here in the input, and we have a kind of initial conditions. Also the output is 10 to the minus 18 in this moment. This is practically 0. What if we want to have a second order system? Okay, I'll put this animation off. I go offline. The only thing that we have to do is to, for example, copy this block, and paste here on the right hand side of the network, and we have this way 2 lead lag blocks. But the thing is that this second lead lag block has the same instance data block, and this is not going to work. Then I will delete it, and we better create it from 0. We drag the lead lag block here to the right hand side of the network and put another instance block, for example instance block number 3. We have here db3, here db1, then it's going to function this time. We have manually to fill this actual parameters 15 in order that the second block has exactly the same parameters as the first block. 1.0 for sample time and 1.0 also for the gain. Then var process, I copy this. This is going to come here at the output of the second block, and we have to delete this entry and join the output of the first block to the input of the second block. How can we do that? Here we can define a temporary variable, for example out in. The name doesn't matter, this is only a name. Type, it has to be, of course, real type. Then with this temporary variable, we have the possibility of inserting the variable here, out in, and here same variable, out in. Then we have connected two blocks. Okay, what would happen if we apply a step or a run or any kind of on the first block? This first block is going to have an output response which is going to be transmitted to the second block, and at the end we will have the time response of this second order system with no zeros but two poles here on the right hand side of the second block in var process. But this is going to be discussed in more detail in the next video, where we are going to connect this model of a second order system plan with a PID controller, in the sense that the output of the model, the variable var process, is going to be the input of the PID controller, and at the same time the output of the PID controller is going to be the input here of the plan. In that sense, we're going to have a closed loop system with feedback, and if we alter one of the parameters, for example the set point of the PID, we will see how the system responds, what is the time response of the system, which of course is going to depend on the parameters that we define here on these blocks. Lead time, lag time, that is 0 and pole, sample time, gain, on the same thing for the second part of the second order model. Okay, we are finished with this video. If you have found this presentation interesting, please don't forget to give a like and subscribe to the channel, and I wait you for the next video where we will be discussing the closed loop system of a second order model, this model that we have created here in this presentation, in connection with a controller which is going to be the compact PID controller that offers the TIA Portal software. Thank you very much for your attention, and I wait for you in the next video.